Hey everyone, basically going to be doing a tutorial or a video series really on how to write different algorithms in Cuda. So the first one I'm going to look at is actually just an easy one. It's going to be just finding the maximum in an array using Cuda. So you have a big array, we want to find the max. Okay, so I already got my sort of directory set up here, so let's go. Okay. So what we're going to do first is just create a main file. Yeah, so we're going to be creating a main file, a kernel header file, kernels.cu file, and then a make file. And I already got the make file set up here. Basically, though, yeah, you can see here I've got the code already written out, but just to reference it in case I make a mistake. But yeah, so I'm going to go through it with you guys from scratch. So what do we want to do first? So we're just going to include our usual, yeah, we're going to use this IO stream. We're going to use, I think we're going to use, yeah, stdlib. I think that's how it's supposed to be. So we're going to include our kernels. Kernels, yes. We haven't written this one yet, but we will be including it, so might as well do it there. Okay, so let's write our main function. Yeah, so this is going to be, this first video is just on a simple kernel or a simple example finding the max in an array. But as the series goes on, I'm just going to keep adding more videos, you know, doing more complex algorithms and trees using CUDA and that kind of thing. But anyways, so we're going to want to create an array of size n, so we'll define our n, and I think I'll do just 1,000,000, I guess, or about 1,000,000 size first. So we're going to want a host array. So let's just do that. And then a device array. And okay, so we'll do our allocations, our memory allocations. Allocate memory. So for the first one, our host array is going to be just using the usual malloc. Size of float times n. Next one is our Cuda malloc for the device array. What is it? Void. We might as well do our freeing of memory. Free memory. Free array. Okay, so we got a host array, a device array. And oh yes, we're gonna need also a variable to store what the max is when we find it. So we're gonna want one for the host and one for the device as well. So we're finding the max in an array, so this is going to store whatever that max is. So yeah, we'll do the allocations as well. Just size of float. And Cuda malloc. float, and I don't want that n there, that's just one float. Okay, yeah, we'll do our freeze device max. Nope, host max there. What am I doing? And Cuda free. This is the device max. Okay. Okay, so this is the start of our main file, as I've shown you here. So we have these files here that are basically empty. The make file here, so yeah, I didn't want to write this one out because I always forget how to make files, so I just kind of kept it here. Basically, we have the list of our objects, in this case just two, the main.o, and then kernels.o. NVCC our compiler. Just some flags. This one here sets the compute capability of your GPU. So I'm doing mine's 3.0, so that's why it's 3.0. You don't actually have to include this line, but libs, we don't actually have any. Calling the executable main, and then just compiling here. Yeah, hopefully you guys have used makefiles before. It's just a simple one. Okay, so in our empty kernels header file, yeah, also I'm I'm laying in bed right now, so if the yeah, that's it's my pillow back there, and if it shakes, that's because yeah, I'm on a laptop. Okay. That's weird. I don't know if you guys can see that yellow circle there. I don't know why it's not disappearing. Okay, so what do we want to do? If not defined, h define. Nope. And if. So we're only gonna have just one kernel. This is a simple program. So it's gonna be a global void, and then we'll call this find max. Oh yes, already written down. Find maximum kernel. Okay. What's this gonna take? What do we need here? So there's gonna be the array. We're gonna have the size. We're also gonna have what our max is. And then I think actually we're gonna need, do we need this? We'll leave that for now. Okay. Gonna copy this. Okay, this is our kernels. Paste. I don't know why that circle's there, but that's okay. Include kernels.cuh. And let's try and compile this right now. This should work. Okay. Make. So this is why we have the make file. So we're gonna do make clean. Because I already had this build before. So you can see there's our files. Okay, so we're gonna do make std. That's probably because there is no h there. Yeah, I think it's just that. Try that again. Make 17. There was an error. Yep, right there. Silly errors. Okay, make. Still something wrong there. Is it float? What is wrong? Hmax, hrarray. Oh. Malloc. This should work. What's going on here? Invalid conversion. Line 17 and 18. Well, luckily I had this written out down here. Let's take a peek. Oh my god, I'm an idiot. Yeah, okay. Oh, stupid circle. Don't forget that. Yes, that's why. Okay. Let's try this. Yeah, perfect. Okay, I should be able to run it too. Yeah, nothing happens. That makes sense. Yeah, I always use Cuda Mem Check. I don't know if you guys use that a lot. You should. Yeah, 0 errors. Good. Okay. So let's get back in there. Okay, so what do we want to do now? We've allocated data. We need to now do a copy from host to device. So we're going to, oh no, actually first, well, we will do that, but we need to do something first. We need to fill host array with data. So we want to fill the host array with basically, well, we're just going to be doing a bunch of dummy data for this one just because we don't really care. We just want to have some dummy data to test our program with. So let's do this. Host array. What do we want to do here? Let's do float rand. That's why we included this C std lib rand. Well, actually, I think we need this as well. Std. Maybe, I don't know. Let's just include it. Won't hurt. Okay. Rand max, okay. And what we'll do is we'll just multiply by n too. That way it creates just a bunch of data between 0 and n. So when we find the max, it should be close to n. The max should be close to n because we're looking for the max in an array of 0 to n. Okay. So that's okay. Now we can do the copying, I think. Copy from host to device. Okay, how do we do that? We do a Cuda Mem Copy. So we're going from the destination is going to be the device. Source is the host. Size of. Okay. And then this is going to be Cuda Mem Copy host to device. Yes. And then we're going to have a part where we call the kernel that we haven't created yet. And then a part copy from device to host. Report results. Okay. So we need to copy the host array that just has our dummy data. We also, I think that's all we have to copy. The copy back will be copy. Yeah, so when we're going to find the max on the kernel, and then we're going to copy just the max back. We don't need to copy the array back or anything. So in this case, it's going to be The destination is going to be host max. Source is the device max that we found on the device. Size of float. And Cuda Mem Copy device to host. And then for the kernel, grid size. So we're doing 1024 by 1024 length array. Let's just do 256 times 256. You'll see why I'm not doing the same. Like I'm not doing 1024 blocks of size where each block is size of 1024. Instead, I'm going to do smaller number of blocks and smaller size blocks, but that'll be okay because you'll see when we write the kernel that we deal with that. Ooh, what am I doing here? Yeah, sorry, 250, that'd be weird. 256 blocks, and then each block is going to be 256 as well. So you'll see how this works out when we write the kernel. Okay, and what do we call our kernel? Find maximum value. Let's just copy this. Let's do that. And yeah, so when we call the kernel, grid size, block size, 1, 2, 3. Okay. Let's just make sure this compiles. It's good to check frequently. Clear make. Nope. stdlib. Maybe that one has an H. I always forget this. Let's do a peek down here and check. Yes, it does have an H. That's why. Stupid circle. Okay. H. There we go. Should work now. 25. Oh, right there. Forgot my eye. Okay, good. Yeah, still doesn't do anything. That's fine. I mean, that's what it's supposed to do. We haven't written the kernel yet. Okay. So maybe what we'll do, I think everything here is good. This is fine. Let's write our kernel. Okay, let's think about this. So, most kernels are probably going to have our index just representing each thread. So that's going to be thread idx.x plus x. And for this, we're going to want you'll see why in a second. Grid dimension.x times block. You'll see these two, you'll see why we want to have these. Okay. Okay, so we're trying to find the maximum value in a very big array. So for each block, we're going to have a shared memory region, a shared cache, we'll call it cache. And I'll just leave, so this is going to be the size of our blocks, which I'm just hard coding as 256 for now, at least. What do we want to do next? Okay. while index plus offset less than n. So what's this saying? Okay. Initially offset is 0. We will do set plus stride. And we want to find the max. So basically we have this cache region for each block. And so thread actually, this is a better idea. Let's create a temporary variable. Float temp equals 0 plus equals. We're going to use this built-in max function. Temp cache thread idx.x. No, this is not what we want. We want device array index. Okay, so maybe you can see why I've included these offset and stride. So basically, let's say that we had, say the array, the total length of the array was 1,000, and we had 10 blocks of size 10, so each block had 10 threads. Well, 10 times 10 is a total number of threads within our grid that's only 100. But, and even though an array is 1,000, but by having this stride and offset, like thread 0, for example, will deal with the first entry in the global array, and it will deal with the 101st entry and the 201st and the 301st, etc. So it just allows more flexibility, so we don't have to match the number of blocks and block sizes with the size of the array. The size of the array can be bigger, and that's okay. Okay, so hopefully that makes sense. Think about it. So now that each thread has this temp variable that's stored its sort of local maximum for, well, we're going to put that in our cache. Temp, which means we need a sync threads. Okay, then each block has this cache of 256 different values. We then want to find the maximum within those 256. So we need to do a reduction. And to do that, this is kind of like a standard design pattern for Cuda, or parallel programming and reduction. It's going to be dim.x divided by 2. Divide equals. If less than I, then cache, I think, thread idx. Again, using fmax. X Okay. So this is going to basically, for each block that has 256 values, by the end of this reduction, the maximum of those 256 will be in the first entry of the cache. It'll be in cache bracket 0 bracket. So we just need to report that back, or we just need to modify the global maximum to take the max of, yeah, we'll see here. So if we're at the first thread, then yeah, okay. So this is what I was thinking about before. Okay. So say you have 10 different blocks. Each block after the reduction, the first entry in that block's cache is going to be the local maximum for that block. And now we want to further reduce it. So each block updates the global max. But because we're accessing a global variable here, we need to do it atomically. Now the problem is though, I don't think there's any atomic operation for finding maximum. Like there's an atomic operation for adding and copy and swap and that kind of thing, but I don't think there's one for max. And that's kind of why I chose this example instead of say doing like a dot product, because the dot product example is pretty similar to this. So what we actually need to do is include an additional variable here called a mutex. It's just an int. I'll finish writing this part and then I'll go back to the main and kind of explain. Well, we'll see. Oh yeah, I always forget this. It's gonna be atomic mutex 0, 1. So what this says, while, so let's say the mutex is going to only have a value of 0, 1. 0 means it's unlocked, 1 means it's locked. So if mutex is 0, so 0 equals 0, which means then the mutex becomes 1. But we report back the previous value, the initial value that mutex had. So the initial mutex, so while it's equal to 1, I think, is this what we want to do? So if mutex is initially 0, yes, I think this works. If the mutex is initially 0, it'll be equal to this 0, so that passes the test, which means the mutex becomes 1, but initially it was 0, so 0 is not equal to 1, which means we can pass through this. Okay. So if it's initially unlocked, it'll pass this test, the thread will get past this while loop, and then what we want to do is update max to be equal to the f max of itself, whatever's already there, and cache 0. And then once that thread is done its updating, we need to do atomic exchange mutex to unlock it again. Okay, let's let's take a peek and see if I did this right. This is the solution here. While mutex 0, 1, oh, it's not 0. Yeah, that's the same thing. Yeah, we'll just write it the way I did there. It's the same thing. Okay. Let's just check, make sure everything is okay here. I think I did everything right. Yeah, that looks the same. Yeah. Oh, apparently we need SD. Oh yeah, I just had that because I was doing some print statements before. We don't need that. Okay. So I think this is correct. There was one more thing I was thinking of though. we do want, yeah, let's do this here. Let's do it here. Okay, so we want the initial device maximum to be 0. So, Cuda Mem set D max 0 size of float. Just that way, because initially it could have some random value, so we want to make sure it's initially 0. In this case, because our dummy data is just positive numbers between 0 and n. Okay, and then reporting the results. Maximum number is the value that we copied back to the host. And we'll do, well, we'll just leave that for now. Okay, let's try this. Let's see if this actually compiles. Okay, make, yeah, makes errors somewhere. 22. Cuda Mem set. Oh. Oh, whoops. That's stupid. Okay. Kernel 12. 12 and 16. Oh yeah, we called it n, that's that, yeah. And what was 12? Oh, yeah, we need float. Silly. D array at 17, yeah. 17, yeah, just array. Okay. 38. Oh yeah, we have to add our mutex. Okay. So we need to include this mutex variable. It's going to be an int. So this is like a variable that we're going to pass into our kernel. Each thread is going to be using this to figure out whether that last part of the kernel was, whether it's locked or unlocked, so that it could update the global maximum value. So we need to allocate, so it's only going to be on the device. And then we will mem set this as well, so that it's initially 0, so that means that it's unlocked. Okay. And that also means we need to free it. And to actually, to be consistent, let's make it dmutex in here. Dmutex meaning it's on the device. Let's be consistent. And then when we call the kernel, we did it. Where did we do it? Dmutex. Okay, let's try that. Looks Okay, well, compiled. Da da da. Fingers crossed. I think something went wrong. I have to wait for the GPU to time out because I think we're stuck in a while loop somewhere. Should stop eventually. Come on. Wonder actually. There we go. Let's see if what went wrong. Recall the kernel. That's fine. Let's just cheat a bit here. What did I do wrong? Oh, I should probably make this -1. Yeah, just for this case. What did I screw up? That should be fine. Do that sync threads, reduction. Oh, yep. Right here. I've done this before. I can't believe I keep doing this. Yeah, make sure that's that's right. That'll make a big difference. Okay, fingers crossed. See if this works. Okay, it looks like it could be working. To confirm, let's confirm our results by run CPU version here. So if we're doing this as a serial code on the CPU, what would we do? We would do just a for loop, just like a linear search to find the max. If you can use the host array here. Greater than. Loops through each element, checks if that, yeah, I think that's right. Okay, let's report these results back and see that we get the same answer. Found on GPU was. Let's see. Nice, so we get the same answer. So it looks like about, what is that, 1,000,000-ish? Yeah, 1,000,000. If we reduce, it's 32. Do another test here. Yeah, so in this case, 32 times 32, what is that? 32 times 32. Oh, yeah, 1024. 1024, yeah, so our initial dummy data was 0 to 1024, random numbers, floating numbers, so we would expect the maximum would be, since it's uniformly distributed, it would be close to 1024. So yeah, this looks like it's working. Maybe I'll do a few timing results here actually. Let's time this. And then we'll leave. That'll be the end. Fill host. Yeah, so you know what I'll do? I'll just cheat here. Speed this up. Yeah, set up timing variables. Copy this part. So this is just going to allow us to time the GPU code. Need this. So we'll start the timer right before the copy, since like in a serial version you wouldn't have to do this copy, so I think it's fair to kind of include that as part of the timing of the GPU. And then we'll end it after the copy from the device back to the host for the same reason. You know, we wouldn't normally do that in the serial code, so if we're gonna be honest, we should include that as part of the time of the GPU. Okay. And we'll add this to our reporting of results. And I called this GPU elapsed time. GPU. Okay, let's see if this works. Yeah, looks like it is. Except we want to do a GPU elapsed time milliseconds. I don't know if that's how you spell that. Whatever. And then we want to time the CPU code as well. To do that, I don't think you can't use this same, so we're gonna have to use include C time, I think. I don't remember if that's it. Let's check. Cheating, C time. And then we'll do float CPU start equals, actually, is it? It's clock T, I think. CPU start equals clock. Let's copy that. CPU stop. And then float Stop minus start. I think it's divided by clocks per second, but times 1,000, I think. Let me just cheat down here to my already done version. Yeah, it is, okay. The CPU took. Okay, let's try this. Okay. 0. I wonder if that's just because it's too small of a time. Let's try to do a bigger example. Yeah, so in finding the maximum of the array, um, so we will see that the GPU can be faster, but it won't be like super faster because just this type of operation is bound by um, a lot of global memory accesses here. There's not a lot of like computation going on. So for example, accessing this global array kind of takes a lot of time on the GPU, sort of. And yeah, so but well, let's just see here. Let's just make these bigger. 256 blocks by 256 each block size. 256 for the cache. Okay, let's see what happens now. So this is like an array of about 1,000,000 elements. See, why is it reporting 0? I think that's wrong. What's going on here? Let's do some cheating. Start. Stop. One thing we can, to really properly test this actually, let's do this like a whole bunch of times. So we're going to find this max of this array 1,000 times. That's also going to help just to get a bigger sample size, or just to take longer so that we get more accurate measurements. So we do that 1,000 times, and we're also going to do it for the kernel 1,000 times. Let's just copy this. Because I think that's what I did down here. Yeah, did it 1,000 times. That's the same. Stop. Oh, you know what? Maybe this needs to. Oh, I think it's saying 0 because of this. I think that actually has to be that, maybe. Let's find out. Yeah, okay, here we go. Yeah, it was because I had float there instead of clock_t. So the GPU took 745 milliseconds. On the CPU, it took 1,241 milliseconds to find the same answer. So the GPU is faster. It's not like super faster. Normally when people talk about like and using CUDA programs, that like 10 times faster or something like that. But just let me And I mean, part of that is just this example. It's not really a super heavy computational example. That's part of the problem. But let's just make our array a lot larger. So 20 million-ish plus in size, keeping everything else the same. Let's see how this works. I'm hoping this works. Hopefully it's going to be significantly more faster. Okay. So it obviously takes longer. Okay, so the GPU took just under 5,000 milliseconds. CPU is running now. Yeah, you can tell it's taking longer. Oh yeah. Oh man, I hope I didn't make it too big. Okay, there we go. Yeah, so you can see here for that, when you make the array large enough, when there's enough sort of work to be done, the parallel version is definitely way faster. GPU took just under 5,000 milliseconds. On the CPU, that took almost 28,000. So that's 5 point something times slower. That's not like, you can definitely get way bigger speed ups depending on your problem on the GPU. Some problems you can speed up like more than 10 times, but still, this, even for this example where there's not a lot of computation in the example really, it still shows you that the GPU is faster, can be faster if the sample size, or if the problem is big enough. So yeah, I think we'll end this video here. I don't want to make these videos too long. This is going to be, again, a series. So each time we're going to look at different problems. I'm just going to walk through them like this. So even though I have the code kind of finished down here, I'm going to, walk through them with you guys. Yeah, we're going to be doing more complicated ones. I just wanted to start with a simple one. The big thing from this one actually is just this whole idea of using the mutex. So we pass in this integer pointer, and we're using that to sort of, so each thread that kind of runs through this code gets to here, or the zero thread for each block, sorry, gets to here, and then it needs to just figure out, can I proceed to modify this global max float? And it uses this idea of locking. So this is like the lock, and then the unlock through this mutex variable to do that. Yeah, so hopefully you guys understand this. Yeah, just walking through this code. The next video I'm gonna do, I think, is gonna be just another simple one. It's gonna be on using, I think we're gonna find pi, the number pi, using the Monte Carlo method. So if you guys have heard of that, then you'll know what I'm talking about, and if you haven't, I'll explain it. It's basically just using, yeah, we're just gonna find the an approximation to the number pi. You'll see in the next video. Anyways, hopefully you guys enjoyed, and yeah, thanks for watching.